All right, so welcome to day 3 of number 3, and today we're going to be covering some number patterns. So we're going to start off, so here's the topics. We're going to cover modular arithmetic, clocks and time, Pascal's triangle, the Fibonacci sequence, and possibly triangular numbers if we have time. So it's going to be interesting. And we're going to start with the homework review. So here's problem 1. If you guys would like to put your answer in the chat, go ahead now. Even if it's a guess, that's fine. Okay, it looks like this question might have stumped you. So let's go into an explanation. The first step, as always, is to find the prime factorization. So we can easily see that it's divisible by 2 and 5. So we factored those out first, and then we continue going into the larger primes until we finish factorizing it out. And then you can see there, the finished prime factorization is 2 squared times 5 squared times 17 times 19 times 37 squared times 97 times 101. And from there, we know our rule for finding the number of factors is to take all of the exponents in the prime factorization. So for example, for 2 squared, we take out the 2, and then we have to add 1 to all of the exponents. So you can see there in that equation. Then you finally multiply all of those exponents that you added 1 to. You multiply all of those together to get the number of factors. So the answer here is 432. All right. And if you guys have questions at any time, feel free to unmute and say them or put it in the chat. Okay, so number 2, what is the product of the factors of 213,444? Okay, so what do you guys think the first step should be when we're solving this problem? Same first step as always.
Find the factors?
Yeah, perfect. Find the prime factorization. So we do that here, and we get 2 squared times 3 squared times 7 squared times 11 squared as our prime factorization. And so just as a quick review, you can always use a factor tree to find prime factorization, which is a bit easier than writing it all out like this. And then we take the exponents like we did before, and we add 1 to them. Then you multiply all of those together, and that tells you the number of factors. So we have to use the number of factors when we're finding the product of all the factors. Because as we learned on Tuesday, the equation for product of factors is the square root of the number all raised to the power of the number of factors the number has. All right. And so here, we didn't write it all out because that would be like a huge number, but we just found the square root of 213,444, and then we raised that to the power of the number of factors it has. All right, problem 3. How many of the factors of that number are squares? Okay, so first step, find the prime factorization. And now, when you think of trying to find the number of squares, what should our strategy be? Post the link. Do you want like the link to, what do you want the link to exactly? Okay. Oh, homework. Okay, let's see. number theory homework. Day 2. Okay. So the strategy for finding the number of squares, well, you know that any number that's a square has to have an even exponent or an exponent greater than 2, because, you know, if, let's say, a factor of that number is 25, well, then that means that it has to have 5 squared at least in its prime factorization. Yeah, we're on question 3. So when we write out the prime factorization, we're basically looking for like how many of them are greater than 2. So then the number of square factors would be 2 times 2 times 3 times 2, which is 24 square factors. So basically, to explain a little bit further, so for 7, you can see the exponent is 5. And so then there's 3 even numbers that come into 5. There would be 0, 2, and 4. And that's why I put a 3 here. But for like 2, there's 2 even factors that we can have. 2 even powers that we can have, 0 and 2. So we multiply it by 2 because that's 2 possible combinations. And then if we multiply all the combinations together, that tells you like the total number of factors that can be squares. Okay, problem 4. How many factors of that are a multiple of 5? Okay, so the steps here, basically, we find the prime factorization. And then now we have to look at how many of them have 5s in them. So when we're calculating like how many combinations there are, usually the combinations would include like 5 to the 0th power, 5 to the 1st power, and 5 to the 2nd power. But here we don't want to include 5 to the 0th power because that means there isn't a 5 in the factor, but we're looking for which ones do have 5. And that's why 5 is the only exponent that we don't add 1 to. So we just keep it at 2, like the original exponent it has in the prime factorization, while all the other exponents you have to add 1 to. And so that means once you multiply all of those, there are 32 factors of 82 million and so on that are a multiple of 5. All right, so problem 5, how many of the factors of 58,320,000 are perfect squares or cubes? So we're going to find the prime factorization. And now going back to perfect squares, those would be how many have only like even numbers in their exponents, while perfect cubes would require them to have a 0 or a multiple of 3 as their exponent. So for perfect squares, there's 48 possibilities. So let's just go through like the possibilities for 2 to the 7th. We have 2 to the 0th power, 2 to the 2nd power, 2 to the 4th power, and 2 to the 6th power. So that's 4 possibilities, and that's why we multiply it by 4 there. And the same goes for the other 2. And now we're going to find how many are perfect cubes. So again, for 2 to the 7th, you have 2 to the 0th as a possibility, 2 to the 3rd, and 2 to the 6th. That would be perfect cubes. So we multiply the 3 there. And so if we add like the number of perfect squares and the number of perfect cubes, we get 66. But that's not the right answer because some of the numbers will be counted twice, namely like the ones that are powers of 6. So we have to get rid of those. And so basically for powers of 6, you're counting 2 times, you're double counting the ones that are like the powers of 0 and then the powers of 6. So for example, in 3 to the 6th, we multiply by 2 because we need to get rid of the 3 to the 0th that was repeated and the 3 to the 6th that was counted in both. And so that gives us like 4 that we've repeated. And we do 66 minus 4 to find 62 factors that are perfect squares or cubes. All right, so I'm going to go back and review 1 and 2 because some people joined that weren't here. So I'm just going to go over them really quickly again. So how many factors does this number have? This is basically the number of factors rule that we learned. So first you find the prime factorization, and then you take all the exponents and add 1 to them. Then you multiply all of those numbers together to get the number of factors, which is 432 for problem 1. And then for problem 2, the product of factors, well, to find that, you have to find the prime factorization, then find the number of factors, and then the equation for product of factors is like finding the product of factors of 213,444 is the square root of 213,444, all raised to the power of 81. And so our answer, which we don't want to multiply out all the way because that'd be ridiculously large, is 462 to the 81st power. Okay, so let's get to the content for today. So first, modular arithmetic. Have any of you heard of modular arithmetic? Or like, if you have any idea of what it might be, you can type in the chat your guess. All right, so I'll assume it's something new to all of you. So what is modular arithmetic? It's referring to a special function called the modulus function, which is abbreviated as mod. And so what exactly does that do? The mod function just finds the remainder when a is divided by b. So it's written out as a mod b, where like a is the number being divided and b is the divisor. So for a mod b, what you would do is do a divided by b and then find the remainder of that. And that's your answer for a mod b, if that makes sense. We're going to go into some examples. So one example would be like 13 mod 2. All right, so can anyone right now guess what 13 mod 2 equals? Remember, the remainder when a is divided by b. Yeah, okay, so 13 divided by 2 does equal 6 remainder 1. But here, we can just basically ignore the 6. All we're looking for is the remainder. That's the only thing the mod function cares about. So the answer is just 1. So we read that out as 13 mod 2. And then it's asking what is the remainder. So only for remainder. And the answer would be 1. So you can also refer to it as the modular residue. And now we're going to be talking about some number patterns you can find in modular arithmetic, which are commonly asked on the AMC test. So first we're going to list out the powers of 2 here. And do any of you guys notice a pattern in the units digit? Just look at the units digit. Do you guys see a pattern here? Yeah, okay, so the number themselves are doubling because you're just multiplying by 2 each time. But let's just focus on only the units place. So here, only here. And does anyone notice a pattern just like in those digits? Well, the pattern is that 2, 4, 8, 6, and then it repeats. Oh, I didn't circle the 6, but then 2486, 2486, 2486, and that's going to go on forever and forever. No matter what power of 2 you raise it to, it's going to fall into that pattern. Okay. And so, yeah, so the pattern 2486. And since this pattern repeats, let's say a question is asking us for what is the units digit of 2 to the 879th power? Well, obviously, you can't really do that by hand, but you can you can easily solve it using modular arithmetic. So we do 879 mod 4, and that gives us 3. And we do 4 because there's 4 numbers in our pattern, 2, 4, 8, and 6, okay? So that's always the number of numbers in the pattern. And 3 tells us where in the pattern it falls. So 2, 4, 8, 6, and our remainder is 3. So we pick the third number in our pattern. What is the third number in our pattern? You can type it in the chat. Yeah, perfect. The third number in our pattern is 8. And so that tells us that 2 to the 879th power must also end in 8. And so you have a question, Brian? Yes, you're unmuted. Okay. Yeah, you can say like basically all numbers when they're raised to exponents, they will have a pattern. You just have to find it by writing out all the exponents. And so let's say we were doing instead like 2 to the 880th. Well, that would just leave you with a remainder of 0. So if it's a remainder of 0, the number you go to is like the last number in the pattern. That would be a 6 if the remainder is 0. If the remainder is 1, you go to 2, the first number in the pattern, 3, the fourth number in the pattern. 2, the second number in the pattern. And then if the remainder is 0, you just go to the last number in the pattern. So here's an example. Find the units digit of 9 to the 31st. So what should our first step be? Based off the last slide, what should our first step be here?
Find the pattern.
Yeah, perfect. So we need to write out all the exponents of 9 until we find a pattern. So we're going to list it out. 9 to the first power equals 9. 9 to the second power equals 81. 9 to the third power equals 729. So our pattern looks like it alternates between 9, 1, 9, 1 forever. So 9 appears when the power is odd, and 1 appears when the power is even. And since 9 to the 31st has an odd power, this means that it should end in the digit 9. And so basically, if we're going to use this, we can also do this using modular arithmetic. So 31 mod 2, because there's 2 numbers in our pattern, 9 and 1, mod 2. And so that leaves us, what is 31 mod 2? Feel free to type it in the chat. What is 31 mod 2? Remember, it's just the remainder when 31 is divided by 2. Yeah, great. The answer would be 1. So that's, and then we look at the first number in the pattern, which would be 9. So same thing. And so the answer, 9 to the 31st, has a units digit of 9. All right, so when you find a pattern in like the nth digit of a number, you don't need to see if like the following numbers follow the same pattern, because you know they always will. And so here are some practice problems. So go ahead and try them out. Remember, first step is always to try to find the pattern. And it's okay if you're a little bit confused about like finding the remainder and stuff, but just try your best to find the pattern in all of these. And then we'll go over it in a few minutes from now.
I have a question on question number 1.
Yeah.
So I found the pattern, but the pattern basically all the digits end in a 6. So we
Yeah.
can't divide by 1. So
All right, so that's the pattern. So everything ends in 6, and that's going to continue forever and forever. So what do you think 6 to that 6 raised to, so 6 raised to any power is just going to be what? Have
a
what?
6.
Yeah. So that's the correct answer.
Oh,
Good
the
job.
6 would just be the answer.
Yeah, 6 is just the answer.
Okay.
All right. Has anyone found the pattern for 7? The unit digit of 7?
Yeah, I found the pattern, but I'm about to solve.
All right, that's great.
Is a tens digit the same as the unit digit, but it's in like the second row instead of the first?
Yeah, so basically you just like look in the tens place and find a pattern for that. It's gonna be like a different pattern, but basically the same idea.
Okay.
I need I don't know how to do the third problem.
That's okay. We can just, we'll go over it. If you finished with the first two problems, you can feel free to write your answers in the chat.
Okay. Yeah, I'm doing the last problem. 1 second. Found the pattern. Just gotta solve. I finished.
All right. So apologies if you aren't finished, but we're going to have to move on. So the units digit of 6 to the 77,777th power. And so the pattern here is that no matter what power you raise 6 to, the units digit is always going to be 6, like Jivitesh said. So for example, like 6 to the first is 6, 6 to the second power is 36, 6 to the third power is 216. Always 6, so the answer here is this could be 6. Find the units digit of 7 raised to the 401st power. All right, so let's find the pattern for this one. So 7 to the first power is 7, 7 to the second power is 49, 7 to the third power is 343. Okay, and then 343 times 7 is 2,401. Okay, and then we can see if we multiply that by 7 again, the units place is going to end up being 7. So then our pattern is repeating, and we can see that our pattern is 7931. Okay, so that's 4 numbers in this pattern. So we know we have to do 401 mod, I'm just going to write an M, 401, okay, that looks horrible, 401 mod 4. And so type in the chat what 401 mod 4 would equal. All right, good. Okay, so remember 401 mod 4, basically just asking you to divide 401 by 4 and then find the remainder. So we know that 400 is a multiple of 4. So our remainder is going to be 1. And so we use that remainder, the answer we get from our modulus function, and we look in our pattern for the first number in the pattern since our remainder is 1. Well, the first number in our pattern is 7. So our answer is going to be that the units digit will be 7 here. All right. And now for finding the 10th digit. So first we have to find the pattern in the 10th digit, which is written out there, but we can just solve it for ourselves. So 7 to the first power is like 7. So the tens place has a 0 in it. Then the next one is 49. And the next one is 343. So then that's another 4 in the tens place. And then the next one is 2,401. So that's a 0 in the tens place. So our pattern is 0, 4, 4, 0. And then it's going to repeat if you continue after that. So that's another pattern of 4. And we do 401, sorry, mod 4 again. So then that gives us a remainder of 1. And we look at the first number in our pattern, which is 0. So for our answer.
Oh, I got 4400 as a pattern.
4400. Oh, maybe you skipped like 7 to the first power because that didn't have a tens place, but like technically the tens place is a 0.
Oh,
And,
yeah, then I see the
yeah, we didn't
mistake.
go over that, so I wouldn't expect you. So, okay. Now we're going to go into factorials. So if you don't know what a factorial is, basically the format that you write it in, it's like a number followed by an exclamation point. And then you just multiply all the numbers from 1 up to that number. So for example, 3 factorial is like 3 to the exclamation point, and it equals 3 times 2 times 1, or 6. 4 factorial would be 4 times 3 times 2 times 1. All right, and so on. 0 factorial is kind of special because it equals 1, and you can find lots of explanations for why online, but we're not going to go into that. So basically, all you need to know is like, those are the factorials. And so a pattern that you might notice in the last digit of these factorials is that all factorials greater than 4 factorial have their last digit as 0.
I have a question.
Yeah, sure.
Why is 0 factorial equal to 1?
Okay. So let's see. I don't actually know this off the top of my head, so, but there are lots of explanations you can find online if you Google. Okay, so the idea of the factorial is to compute that the number of combinations of a ranging of set of n numbers. Okay, so that makes sense. So say you have 3 things, like how many orders you can arrange that in would be 3 times 2 times 1. And so if there's nothing in your set, you can arrange that one way, just like nothing in the set, if it makes sense. It is kind of like a theoretical thing. So yeah, I'm sure there's other explanations too, so you can feel free to look through that on your own time. But for now, just like, we don't really need to go into 0 factorial. It's not really used in the rest of the lesson anyway. But it's a good thing to search up if you're interested. So the only way you have 0 as your last digit is if you have 10 as one of your factors. And to have 10 as one of your factors, you must have 2 times 5 in the prime factorization. So starting from 5 factorial, every factorial is going to be divisible by 10. And we can also predict how many zeros a factorial will end with if we look at their prime factorization. So the number of tens in a factorial is determined by how many 2s and 5s are in its prime factorization. But so there's going to be way more 2s than there are 5s because there are more even numbers than there are numbers divisible by 5. So 5 is our limiting factor here. And so it's going to determine how many tens are in the factorial. So let's say we're trying to find how many how many zeros are at the end of 11 factorial. And so we find the prime factorization of it, which is like, if we write it all out, 11 factorial is 11 times 10 times 9 times 8 and so on. And so if we factor all of those numbers out, we get that as our prime factorization. So now we're looking at how many 5s does that have? Well, it has 2 5s, as you can see. So it's going to end up with 2 zeros. And you can see further yourself that 11 factorial ends up with 2 zeros because there are 2 10s. It's also divisible by like 2 10s. Well, let's try that again. What about 26 factorial? How many zeros is that going to end with? You would think that like 26, you can just do 26 divided by 5, and then it has 5 whole 5s in it. Because thinking about it, 5, 10, 15, 20, 25, wouldn't it just be 5? But that's actually not the answer, because 26 factorial is going to have like 26 times 25 times 24, and 25 equals 5 squared. So there's another 5 that we missed, and there's actually 6 whole 5s in 26, and it ends in 6 zeros. So, so we need a rule to find out how many zeros a number can end with. And to do that, we find x divided by, so we're finding how many zeros are in x factorial as like a general rule. We first find x divided by 5, round that down to an integer, and add that to x divided by 5 squared, round that to an integer, add that to x divided by 5 cubed, round that down to an integer, and so on until one of the integers rounds down to 1. So where basically it's like the power of 5 is bigger than the x, And actually, this works for all prime numbers, not just 5. So if we're trying to find how many times a prime number a appears in the prime factorization of a factorial x factorial, then our strategy is to find x divided by a, round that down to an integer, plus x divided by a squared, and so on, always rounding down to an integer and just adding it until it rounds down to 0. So now we don't even need to find the entire prime factorization to know how many times a number a goes into that number. All right, so some practice problems. How many zeros do the following numbers end with? So you can go ahead, okay, we're gonna go through all of them out, and you can go ahead and try it. So basically, remember, just do like the x factorial divided by a, where a is like the number you're trying to find, and then go on to a squared and so on. And also another hint, if you're looking for the number of zeros, you're basically looking for the number of 5s. That's an easier way to do it. Okay, how are we doing on the first couple? Has anyone found the answer for 3,200 factorial? Or would you like for me to like go through it step by step?
I got the first one, but I don't know if it's correct.
All right, or you can go ahead and type it in the chat.
Okay.
Okay. It looks like that's not quite correct. So let's go ahead and explain. Because we haven't done too much practice on this so far. So we're trying to find, for number of zeros, we're trying to basically find the number of fives. And so to do that, first, we're going to do 3,200 divided by 5, which is going to give us 640. Okay, that's your answer. But then we're undercounting because there's also going to be a lot of like 25s, numbers divisible by 25 inside that factorial. And so those would have like 2 5s because 25 is 5 squared. So we need to count all of those as well. And so we do 3,200 divided by 25. And we have to add, that equals 128. So we have to add that to that. But then we're also missing the numbers divisible by like 125, which is 5 cubed. So we have to divide 3,200 by 5 cubed, which gives us, it gives us 25.6. We have to round that down because you can have like 0.6. And then now we're going to do, but now what about 5 to the 4th power, which is 625? We need to count all of those possibilities as well. So 3,200 divided by 625 rounds down to 5. And then we still have one more step, 5 to the 5th power, which is 3,125. And so only one of those is going to fit. And after that, we don't have to do 5 to the 6th because that's bigger than the original factorial we're going for. So it's not going to work. And then we sum up all of those numbers. And what do we get? We get 799. Yeah. So that's how you do it. And then you just apply the same thing to the other ones. So those are smaller numbers. Okay, so go ahead and try applying that same strategy to 130 factorial and 31 factorial. And you can go ahead and type your answers for the 2 other problems once you found them. All right, in the interest of time, I think we're going to have to move on. So sorry if you didn't quite get done, but if you did get some answers, go ahead and put them in the chat like right now in the next couple of seconds. Okay, so how many zeros do these factorials end in? Well, like I explained, okay, that should say 799, so sorry about that. But like I explained, that's how you do it. You have to find divided by 5, divided by 25, divided by all of the powers of 5 until they get too big. And so same thing for 130 factorial. You divide it by 5, divided by, and then add that to 130 divided by 25, add that to 130 divided by 125. And you're rounding everything down. And so then your answer is going to be 32 zeros that 130 factorial ends in. And so 31 has the same principle, but you only go to like 25 because it's kind of a small number. And so you can't do 125 because 31 divided by 125 would be less than 1. So that's not even a possibility. And this has, you can apply the same rule for any prime, not just 5. So if we're finding the number of 2's in the prime factorization of 17 factorial, we do 17 divided by 2 to the first power plus 17 divided by 2 to the second power, which is 4, plus 17 divided by 2 to the 8th power, 2 to the third power, which is 8, and so on until you can't do it anymore. So that answer would be 15. Then you basically just do the exact same thing, except for you do 3. You do 3's for the last problem. Okay, so another topic we're going to cover today is clocks in time. And so a lot of tests will basically ask you like the angles, the degrees, or how long it's going to take for something, for the angle on a clock between the hands to get to some certain degree. So as you guys should know, 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds. And on a clock face, since clocks are circles, and circles have 360 degrees. So 1 hour makes the hour arm travel 30 degrees. 1 minute makes the minute arm travel 6 degrees, and it makes the hour arm travel 0.5 degrees. And during 1 second, it passes 6 degrees on the second hand. So I suggest you guys write down like this bottom half of the notes here, because we're going to use them in a bunch of problems. So I'll give you a minute to write that down. So clock problems basically talk a lot about like 2 hours has passed. What is the angle between the hour and the minute hand or something? It's like 6:30. Find the angle between the hour and the minute hand. but we're going to go into a bunch of them in a second, so you'll see.
I have a question.
Yeah.
Why does it equal to 0.5 degrees on the hour arm, like for each minute?
Okay, so so the hour arm, it would move 30 degrees per hour. And then there are 60 minutes in an hour.
Yeah.
Yeah, so 1 minute. So we can okay, let me just set up like a ratio to make this look better. So 1 minute over this is like the time ratio. So this is 1 minute and this is 60 minutes. And so then 60 minutes, we're looking at this one. So 1 hour equals 60 minutes. So 60 minutes, it moves 30 degrees. And so then 1 minute, this is like dividing by 2. So we also divide the top half by 2, and then that gives us 0.5 degrees in 1 minute. Does that make sense?
Yeah.
All right, good question. Okay, so I think everyone pretty much should have finished writing that down. So I'll move on. Let me erase this one thing I wrote. Okay. Oh, whoops, I forgot, but I don't think that one's important. Just write it down really quick. 1 second equals 0.1 degrees on the minute hand. Okay. Oh, okay, you know what, we're gonna skip that. I don't think that's important. Yeah, we're not gonna use that, whoops. Okay, so how far in degrees will the hour hand travel in 12 hours? You can type your answer in the chat based off your notes. Yeah, but let's pretend like you didn't see. Okay, type out like your math for why it works, and then type out your answer. Yep, perfect. So the hour hand travels 360 degrees in 12 hours. And also if you just think about it, so let's say like 12 hours is half a day. So it's going to go around the full circle from let's say like midnight to noon. It's going to go around the full circle of the clock. Okay, how far will the minute hand travel in 2 minutes? Yep, you're exactly right. It will be 12 degrees because it travels 6 degrees in 1 minute and we're doing 2 minutes. So it's going to travel 12 degrees. Okay. How far will the hour hand travel in 2 minutes? Okay, this one is a bit trickier, I'd say. The hour hand will travel 1 degree in 2 minutes. So let's see the previous page. Here you can see that 1 minute, it's going to travel 0.5 degrees on the hour arm. So 2 minutes is going to travel 1 whole degree on the hour arm. Yeah, so a bit trickier than once. But good job overall. So some harder questions. How long will it take the hour hand to travel 45 degrees? All right, I'll give you guys 2 minutes to try this out. You should set up a proportion to solve for this. That's the easiest way. Yeah, 1 hour, 30 minutes or 90 minutes is correct. And so Jivitesh did it really fast. So I'm guessing, correct me if I'm wrong, but I'm guessing the method he used is that like 1 hour travels 30 degrees. And so then it takes half an hour to travel the extra 15 degrees. So then he just like added those together. But you can also do this using a proportion, which might be a more direct way to see it. It might be a little bit slower in this situation though. So we use the rule that like 1 minute equals 0.5 degrees. And then so how many minutes are going to be 45 degrees? Well, we can solve this ratio using cross multiplication. So 1 minute times 45 degrees divided by 0.5 degrees is going to give you 90 minutes as your answer. All right, so good job if you got that. And now one more similar question. How long will it take the hour hand to travel 75 degrees? Yep, exactly. The answer would be 150 minutes or 2 hours and 30 minutes. So again, you can do this using a proportion. So another way to solve a proportion is to see like the denominator, 0.5 degrees is getting multiplied by 150 to get to 75. So you also have to multiply the top by 150 to get 150 minutes as your answer. All right, so we're running a bit short on time. So here's a harder question that looks more similar to what you're going to do on the AMC. And so I'm going to walk you guys through how to do this one. So at 12 a.m. midnight, the angle between the hour and minute hand is 0 degrees. They're right on top of each other, pointing at 12. So how long is it going to take for the hour and minute hands to create a 33-degree angle? All right, so this one is different from the other two because the hour and minute hands are moving together, and you have to calculate both of them. So for every minute, the hour hand moves 0.5 degrees and the minute hand moves 6 degrees. So if they're doing that, then every minute, how many degrees apart are they getting? Check that in the chat. Guess how many minutes apart they're moving. I'm sorry, how many degrees apart they're moving every minute? Or basically, like how much faster is the minute hand going? right, so the angle between the hands increases by 6 minus 0.5 degrees every minute. So, okay, so think about it, like in 1 minute, the hour hand is moving 0.5 degrees, the minute hand is moving 6 degrees. So it gets 5.5 degrees like away from the hour hand. And so the angle between the hands after m minutes is 5.5. So now you have to figure out how many minutes m is. And so you're trying to get to a 33 angle. So 5.5 m equals 33, because that's how much it moves per minute. And so what does m equal? Solve that equation. What does m equal? Type it in the chat. Yeah, m here equals 6. So this is basically just solving a variable. You divide both sides by 5.5, and 33 divided by 5.5 equals 6 minutes. So the answer to this question is going to be 6 minutes. And basically just remember, like doing this, you have to calculate the hour and the minute hand using like the rules you've written down and find the difference between them. Okay, so it is time for our 5-minute break. And you're free to do whatever you need to do in these next 5 minutes, but return at 10:40. So I think next up are some AMC8 problems over like the number patterns, modular arithmetic, and clocks that we've just covered. So problem 1, what is the measure of the acute angle formed by the hands of the clock at 4:20 p.m.? So if you don't know acute angle, it's basically like whichever one is smaller, so the angle between them, and it's less than 90 degrees. All right, think about it for a second. Okay, so imagine a clock at like 4:20 p.m. So what would it look like? 0 degrees is when the hands are right on top of each other. So at 4:20, are the hands going to be right on top of each other? They're going to be pretty close, but not on top. Because the hour hand does move. So the hour hand's not going to be pointing directly at 4. It's going to move a little bit past 4. And the minute hand's going to be directly at 4. Okay, so one approach to solving this problem, the answer is D. So one approach to solving this problem is to know that like the hands are going to be together, like straight up and down together at 12 o'clock, no matter whether it's 12 p.m. or 12 a.m. They're going to be right together then. So then you just calculate how far they moved in that 4 hours and 20 minutes. So using our rules, the hour hand travels 30 degrees per hour. And so 420 is 4 1/3 hours. So 30 times 4 1/3 equals 130 degrees. And the minute hand, okay, so the minute hand is going to travel 360 degrees in an hour. And so there's going to be like 20 minutes. So it's going to be at 120 degrees. And so now you just have to find the degree difference between them. So 130 degrees minus 120 degrees equals 10 degrees. So the answer here is D. And clock problems are basically like half thinking, half just remembering these rules so you can do it faster. Although it's also pretty easy to like derive the rules yourself if you put some time into it. Okay. So what is the remainder when 1,999 raised to the power of 2,000 is divided by 5? Is it going to be A? So the strategy for solving this problem is to use like the what you learned about finding the units digit of the number. So you're trying to find the units digit of one of that number, and then it's pretty easy to see the remainder when divided by 5, because basically you look at the last digit, and numbers divisible by 5 end in 5 or 0. So you're seeing how far away it is from 5 or 0. But we'll go through it step by step. So the answer here is going to be B, a remainder of 1. And so first we find the units digit. So to do that, we have to find the pattern. And the pattern here is going to be 9, 1, and forever and forever, 9, 1, 9, 1, 9, 1. So then we do the modular arithmetic. And since 2000 is even, it's going to give you a remainder of 0. So then the last digit of that is going to be 1, because remainder of 0. So that you go to the last digit in the pattern. Oops. And so if there's a remainder of 1, when something is divided by 5, you're going to have a remainder of 1 as well. Because like imagine 61 divided by 5, you have a remainder of 1. 31 divided by 5, you have a remainder of 1. So you can see that the answer is B without doing the math. All right, and what is the tens digit of 7 to the 2011th power? So basically just find the pattern. We actually did already find the pattern for the tens digit of multiples of 7, but you should be able to find it again. And then just do modular arithmetic. Yeah, great. The answer is D. You are correct. So what pattern did you guys find for this question? For the 10th digit of 7 to powers of 7.
I found 0440.
Yeah, that's exactly correct. So just as another explanation, to find the pattern, well, the first number is 7 to the first power, which it has a 0 in the 10th place. Second one is 49, which is 7 squared, so that has a 4 in the 10th place. Second one is 343, so another 4 in the 10th place. Oops. And the last one is 2401, so another 0 in the 10th place. And then the pattern will repeat if you continue solving for it. So knowing that pattern 0440, knowing that pattern, then we do 2011 mod 4 because there's 4 numbers in our pattern. And so that gives us 3. So now since our remainder is 3, we know the last digit is going to be the third digit in our pattern, which is this is the first one, second one, third one, 4. So great job, you got D. And now we're going to skip over this one because there's some more important stuff to learn, but you can feel free to come back and do the problems in here on your own because they are good practice. So Pascal's triangle. This is an interesting sort of math kind of puzzle. So in Pascal's triangle, each number is the sum of the two numbers above it. So if you see here, so 2 is the sum of 1 and 1. We'll take 15 here. 15 is the sum of 10 and 5. 84 is 28 plus 56, and so on and so on. So this could go on for infinity. And it has a lot of interesting patterns that we can point out. Okay, and also here's a rule. So the sum of everything in the nth row, the top row is going to be the 0th row, and the sum of the nth row is going to be 2 to the n, 2 raised to the n power. So for example, okay, so let's put some annotations to make this easier. So this is the 0th row. The top row is the 0th row. This is the first row. This is the second row. This is the third row. And so we'll just solve for the sum of the numbers in the third row. And that's going to be 2 raised to the third power. So you can see that 2 raised to the third power is going to be 8, and 1 plus 3 plus 3 plus 1 is also 8. So this pattern does work. And it's more useful for like saying you need to find the sum of the 22nd row. You can't just add it up. All right, so you can see that rule in play. And remember, the top row is going to be the 0th row. Okay, here's another interesting pattern. So we choose some numbers along the diagonal, like a straight diagonal down. So 1, 6, 21, 56. And then the number directly below it in the opposite direction is going to be the sum of all the numbers. So here's our diagonal. And the number directly below it in like the opposite direction of the diagonal, here's 84. 84 is the sum of all of these numbers right here. And so we can like take another random diagonal. So let's see, we'll take this diagonal. Oops, don't need to do the eraser. We'll take this diagonal right here. What the heck? This diagonal right here. These numbers. And then we have to go in the opposite direction of the diagonal. And this is going to be the sum of all of that. You can type all of that in your calculator if you want, just to check, to see if 35 is the sum of all of these numbers in this diagonal. Or you can add it up in your head. That's pretty easy to add up in your head. And it is true. So it's something called like the hockey stick because it kind of looks like a hockey stick. All right, and here's another pattern. So along the first diagonal is going to be just ones. Second diagonal are the counting numbers, also sometimes called the natural numbers. That's basically all of the numbers besides 0 in just in order, like how you would count. The third one is the triangular numbers. So these are numbers that can be arranged into a triangle formation. Then tetrahedral numbers and pentalope numbers. So yeah, just a bunch of patterns and so on and so on. Okay. And one more interesting pattern is the Fibonacci sequence. All right, how many of you guys have heard of the Fibonacci sequence? You can type yes, no in the chat. It is pretty famous. Has anyone heard of it? All right, you guys have. So we're just going to review, or for those people who haven't heard of it, how do you get the Fibonacci sequence? So we're going to start with 2 1s, and then you add those numbers together. So each subsequent number is the sum of the 2 previous numbers. So here's the pattern. So for example, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, and so on for forever. You just take the sum of the last 2 numbers to get your next number. So there aren't many applications of this, but some problems will ask you to find like the nth term of the Fibonacci sequence or a similar sequence. So it's good to know. So here's an example from the actual AMC 8. And so it's not about the Fibonacci sequence, but it's basically something really similar. A sequence of numbers starts with 1, 2, and 3. The fourth number of the sequence is the sum of the previous 3 numbers in the sequence. So 1 plus 2 plus 3 equals 6, and that's the fourth number. In the same way, every number after the fourth is the sum of the previous 3 numbers. So what's the 8th number in the sequence? All right, go ahead and try and find the 8th number on your own. Oh, and here are your answer options. Remember, we're trying to solve for the 8th number in this sequence. 11 is the 5th number in the sequence. Okay, all of you are saying A, which is interesting because the answer is in fact not A. So since there's only 8 numbers we need to find, we can manually calculate the answer. So A, 11 is actually the 5th number in the sequence. Remember, we're trying to find the 8th number. So 20 is the 6th number, 37 is the 7th number, and 68 would be the 8th number in the sequence. So the correct answer here would be D. And you can see the full sequence right there, where you're just adding the previous 3 numbers to get the next number. Okay, So now we're going to have a fun activity, which is going to be a Kahoot over all the concepts we've covered. So I have it open here. And all right, you can go ahead and join. I'll put the pin in the chat. Oops. These are some great names, guys. All right, join if you want to take part. Okay, there are 7 of you guys other than me, and only 2 people have joined the Kahoot. So remember, pin is up there. Okay, so I'm going to go ahead and start, and you can feel free to join whenever in the middle if you'd like. Okay. What is 3 mod 7 asking for? Yeah, great job. 3 mod 7 is asking for the remainder when 3 is divided by 7. What is 173 mod 7? Okay, so the answer here is going to be 5. So let's see, just for a quick explanation. So 173 mod 7 is just asking you 173 divided by 7, and then you need to find the remainder of that. So 103 divided by 7, you're going to have 24, remainder 5, because the closest multiple of 7 to 173 is 168. So your remainder is going to be 5. And remainder is what the modulus function is asking for. Okay. So what would the sum of the tens and units digit of 2019 to the 2 raised to the 2021 power? So we can see that here this is going to be our pattern. So if we look at the units digit, well, the pattern is going to be 91919 forever. So since so we do 2021 mod 2 because there's two numbers in that pattern, that gives us a 1 as our remainder. So we know that the units digit is going to be the first number in our pattern, or 9. Then we look at the sum of the pattern for the tens place. So that's going to be like these whole 10 numbers right here. And so 2021 divided by 10 is going to be leave us a mod of 1. So, and then the first number in our pattern is 1. So the answer here is 10 because 9 plus 1 equals 10. Okay. So both of you got it correct. But let's just go over this. So the last two digits of 29 to the 801st power. So you can see that the units digit has a pattern of 91991, and 801 mod 2 is gives you a remainder of 1. So it's going to be the first number in our pattern. The units digit is going to be the first number in our pattern. And then you also know that the tens digit is going to be 2, because that's also going to be the first number in our pattern. 801 mod 10. So last digits are going to be 29. Okay, the sum of the last two digits of 29 raised to the 32,849th power. So again, we can see that this is going to have, there's two numbers in our pattern of the units digits. And so that's going to give you a remainder of 1 when you do that exponent mod 2. So that's going to give you the first number in our pattern, which is 9. We know that the units digit is going to be 9. And then now for the tens digit, well, there's 10 numbers in our pattern right here. So we do 32,849 mod 10, and that gives us 9. So we look for the ninth number in the pattern, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that's the ninth number in the pattern. So it should only be like the 6. So that's the last two digits of the number. And if you add them together, you get 15. Okay. So the sum of the numbers in the 8th row of Pascal's triangle. So we know that the rule for this is going to be 2 to the n, where n is the number of rows. So 2 to the n equals 8 right here in this question, because that's what it tells us. Oops. And so 2 to the 8th equals 256, like you guys put. I don't know why I'm writing in Zoom instead of writing on the Jamboard, but oh well. Okay. How many zeros does 130 factorial end in? I think we actually had this problem, like this exact problem. Okay, so how many zeros does 132 130 factorial end in? The strategy here is to find the number of fives in the prime factorization. And to do that, we have our trick where we just do 130 divided by 5 plus 130 divided by 25 plus 130 divided by 125. Okay, so now I need to solve for that. So it's going to be 26. 26 plus 5 plus 1. And we don't go any further because the next one is going to be 625, which is larger than 130. So that's not going to work. Yeah, that's not going to work. And so our answer is 32. Okay, so the largest power of 3 that divides 130 factorial. So basically this is like an exponent of 3, so that'd be like 3 to the 62nd power. So basically let's go over how to do this one. So 130. This is asking like how many 3's are in its prime factorization. So 130 factorial divided by 3 plus 130 factorial, I'm sorry, not factorial, just 130 divided by 9 plus 130 divided by 27 plus 130 divided by 81 plus, okay, you can't go any further than that. So you do that, you round down to the nearest integer, and then you find the sum of all of that. And so that will give you your answer. Okay, so let's see. All right, great job, Bob and Kahoot. You were Kahoot. Okay, nice. So I think we can go back to this because we still have some time left. So I put the link in the chat and you guys can join. You guys should join. And we're going to go over some problems. We might not get through all of them, but just a few. All right. So, like it says over here, use sticky notes to show your answer. And if you have a question, you can type it in the chat or unmute. So calculate 506 mod 7 is the first question.
Is it okay if I put my answers in the chat because I can't join?
Yeah, that's perfectly fine. I know Jamboard can be like laggy for some people or just not work at all. Okay, great. So the correct answer here is 2. So good job, you guys. And just for an explanation, 506 mod 7, you're just looking for the remainder. And so the closest multiple of 567 is going to be 504. So if you divide it, you're going to have a remainder of 2. Yeah. Okay. What is the 10th digit of 7 to raised to the 456 power? So 7 to the 456 power. And we've already found the pattern for this twice now. So maybe you guys even remember it. And all you have to do is find, use modular arithmetic. Okay. So have you guys found the pattern yet for the 10th digit?
Memorized. I know what the pattern is, but when I did the math, there is no remainder.
Oh, right. Okay. So that might be a little bit confusing. So the pattern is going to be 0, 4, 4, 0. We found that a bunch of times, right? And so if the remainder is 0, it's just going to be the last number in the pattern. Because kind of if you think about it, like, so you're doing 456 mod 4. And you can't actually have like a remainder of 4 because that doesn't work. It would just be like an extra in your quotient you wouldn't have it as a remainder because the remainder always has to be smaller than the divisor. That's a 4, if you can tell. So basically, if the remainder is 0, it's going to be the last number in the pattern. And the answer here is 0. Okay, moving on. How many zeros does 50 factorial end with? Okay, yep, 12 is the correct answer for this. So basically, strategy is to find how many 5s are in the prime factorization of 50 factorial to find how many zeros are going to be at the end. And so to do that, we have our rule where we just keep dividing it by powers. So 50 first divided by 5 to the first power, then we add that to 50 over 5 to the second power, and we would continue, but 50 is smaller than 5 to the third power, so we don't need to do it. And so this gets you 10 plus 2 equals 12 zeros. It's going to end with.
Wait, I have a question about this.
Yeah, sure.
Why can't you divide by 10?
Okay. So you can't divide by 10 because you're going to miss a lot of the zeros. So just kind of as an example, let's do, use the text box. Let's do 11 factorial equals 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times. Okay. So you're right that like 10, if there's a 10 in the prime factorization, it's going to have a 0 at the end, right? But then also
Yeah.
you have to count all the 5s in there. So there's going to be a lot of random like 5s and 2s that you can combine together to get another 10. And so if you only count the 10s, you're going to miss that. So we count the 5s instead. So maybe
So you
11.
can only count, so you can only count the 5.
Yeah, we just count how many 5s there.
And
Because,
25. We don't count anything else, just 5s and 25s.
So like in this 10, there's going to be a 2 and a 5. So if we just count the 5s, we're just going to get like 1 5 in this 10. So that's the correct number of zeros because this 10 is going to contribute 1 0. So if we count the number of 5s, sorry, we're going to get the number zeros. And then for 25, we also have to count it 2 times because there's going to be 2 5s in that. And then you like.
So we only count 25 and 5.
And we also have to count like 125, like all multiples of 5. But then 125
Okay.
doesn't matter here because we're only looking at 50 factorial and there's not going to be like 125 in that.
Okay, so we go by 525, 125, 225 in those.
No, it's just the, sorry, my voice. So the numbers in the denominator are just going to be powers of 5. So this is 5 to the first power, this is 5 to the second power, this is 5 to the third power. And then we're also going to do 5
Oh,
to the fourth power if it's a bigger number. And it's going
okay. Okay, now I understand. Thank you.
Yeah, okay. So now for, we're just not going to do the rest of the problems in there, but you can feel free to do them by yourself if you want. And we're going to have homework as usual. So it's going to be posted in Classroom. And also these slides are. So here are the homework problems. And so you should just spend 10 to 15 minutes and do as many of those as you can. So yeah, tomorrow we're going to learn about number bases. And if you guys have any questions, feel free to ask. Otherwise, you can leave.
Bye.
Bye.
Bye. Tomorrow's the last class, right?
Yeah, last class of number theory. And there's also another week to this course. So if you signed up for something there, you're going to go to a different class.
Okay, then bye.
Bye.